enormous pleasure to welcome you all to the Birch Aquarium at Scripps Institution of Oceanography, to the latest Perspectives on Ocean Science lectures, the Jeffrey B. Graham Perspectives on Ocean Science lectures. And it is my great pleasure to welcome our speaker this evening, Dr. Kimberly Prather. Kimberly holds a joint appointment as a professor in the chemistry and the biochemistry department and the Center for Atmospheric Sciences at Scripps Institution of Oceanography here at UC San Diego. And she moved here from UC Riverside in 2001. I spent a year at UC Riverside, and we've been talking about that. She obtained her BS and her PhD from UC Davis in physical and organic chemistry. Between 1990 and 1992, she did postdoctoral research at UC Berkeley in the laboratory of the Nobel laureate Dr. Yan T. Lee. So she's really been to a lot of the UC campuses, which is something not many people have done so many. Both her graduate and postdoctoral research involved detailed investigations of the photodissociation dynamics of organic particles, organic molecules, I should say. And when she became a professor, she shifted her research into the area of heterogeneous chemistry with a focus on problems in aerosol chemistry and climate. And she and her research group developed a unique technique for measuring the composition of aerosol particles in real time, which is used in the studies of pollution and climate change and understanding the health effects of particulate matter in locations around the world. She's received a large number of awards for her research, including the American Society for Mass Spectrometry Research Award, the National Science Foundation Young Investigator Award, the National Science Foundation Special Creativity Award, and I could go on and on. But when she's not working on her research, which I suspect is probably not as often enough as she should, she enjoys spending time. That came out wrong, Kim. What I mean is you work so hard. She spends time with her husband and her 7- and 4-year-old boys, hiking, gardening, and cooking. And I'm really looking forward to her talk tonight because I find her research absolutely fascinating. And so she's going to talk about California's atmosphere, analyzing the air that we breathe.
As Nigella indicated, I moved to UC San Diego 5 years ago from UC Riverside, and I have to say, given the research that I was working on, Riverside was a great place to start my career. And I will, you know, it made us look great. The instruments we initially built weren't quite perfect, but we looked darn good because there was so much to measure. And then we moved to San Diego. And one of the things, our instruments, you can actually tell when they're tracking pollution. You can hear them firing their lasers, and you hear this. In Riverside, it was always like, they're just constantly going. Moved to San Diego, and they went tick, 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 tick. So we had to build better instruments. So I guess that's a good form of job security. So anyway, what I'd like to talk about tonight is just to give you a brief background on the type of air pollution research that we do in my lab. A little bit on the health effects and concerns, in particular with respect to aerosol particles in the atmosphere. And then I'll mainly focus in on, for this talk, on the California perspective. What do we know about air pollution? What are our concerns? And how are the measurements that we're doing in my lab actually helping California figure out which pollutants we need to regulate better. So that will basically tie in. One of the themes I hope to get across tonight, the title of my talk sort of focuses in on air pollution, but the instruments that we use, we focus on air pollution as well as sort of the link. There's an inherent link that you can't get away from, actually, between things that cause air pollution, changing our climate, and then affecting our health. And I will come back to that theme time and time again throughout the talk and show you there's a nice circular logic, which is good because if we can our approach has been to sort of focus on taking care of the air pollution, understanding where the major air pollution sources are, and then controlling those, and then in turn, those actually will help alleviate some of the stress on the system due to climate change, as well as health effects. So the technique that Nigella mentioned that we developed is a technique that the acronym we call ATOF-MS. It's an aerosol time of flight mass spectrometer. And what it does is it allows us to measure the size and chemical composition of individual aerosol particles in the atmosphere without collecting them on any substrate. So we can actually, our golden goal has been to actually use this to sample air directly into the instrument and in real time see what's in the air that we're actually breathing. And nobody had actually been able to do this before, so this was sort of our golden target, and we've finally gotten there. So I will describe some of that research. I'll also talk about some of the recent research where we've been focusing our measurements on the Scripps pier and the reasons and motivations behind that. And then I want to finish with talking about sort of what have we learned from our measurements, where do we stand as far as air pollution and climate, where are we heading as far as these things, and then what can we do to help now. And one of the things I want to stress is if we can figure out ways to alleviate air pollution, that's helping now, versus by doing these same changes, we'll be helping future generations with respect to climate. So just the strict definition of what constitutes air pollution. Basically, air pollution designates the collection of substances that adversely affect human health, animals, and plants, and in general affect our overall quality of life. The major air pollutants that you're used to hearing about when you go in to get, for example, your car smogged are the gases. And so when we talk about a very high pollution day, we're usually actually not something that's measured from your car because it's a secondary pollutant that's formed in the atmosphere. We're usually talking about ozone, but a lot of other things that get emitted from industry and various activities that I'll discuss: sulfur dioxide, nitrogen oxides, carbon monoxide, carbon dioxide, hydrocarbons, or volatile organic, you'll hear VOCs. That was a lot from like evaporation of fumes when you were filling your car, and that's the reason you have those little things around the neck to stop. That was actually a lot of pollution, causing a lot of pollution in California and other places. And if you go to other states, you'll see that a lot of them don't have those, and so they've still got these issues, and I'll talk about what are the implications about that in a second. But the topic that's near and dear to my heart are actually focusing in on the aerosols. We understand a lot more, both with respect to climate change and air pollution, on how gases, in particular for climate, how greenhouse gases are affecting our environment. The aerosols are really the uncertain part, in part because they're very hard to measure. Basically, the sources of aerosols are produced by combustion. I'll talk about some more examples in a second. Windblown dust, sea spray are some examples. I'll give more in a minute. Negative environmental impacts, these are what end up leading to acid rain, nitric acid rain in particular on the West Coast, sulfuric acid rain on the East Coast, climate change, and affect human health. And one of the things I'll focus on, particles as opposed to gases. Gases you tend to breathe in and you breathe right back out again. Particles can go in, they go in with such momentum that they go in and get stuck way down, especially the tiny ones, way down deep in your lungs. And then those can be transported to every single organ in your body, including, it's been shown most recently, they can get transported to your brain. So there's a lot of concern because these are just great transport mechanisms for getting pollutants into your bodies, and we're still trying to understand the health effects. So what does EPA and the state of California and other states regulate? PM, particulate matter regulations, what we call PM 2.5 and PM 10. And what this means is the mass. You basically collect these on a piece of filter paper for a set amount of time and you weigh it. And so what you weigh is the mass of all particles less than 2.5 microns in diameter and less than 10 microns in diameter. There are two different standards because these actually come, for the most part, especially the larger ones, come from different sources. So this was really shocking to me as a chemist that, the way that this is described is it's focusing in on a mass. It doesn't care what the chemistry is. And the chemistry from a health effects perspective, even from a climate perspective, has got to be huge. And so the question is, when I teach my environmental chemistry class, I always ask my students, would you rather be walking on a beach breathing, 20 micrograms of sea salt, or would you rather be sucking on the tailpipe of a diesel truck? And so it's, pretty intuitive that this type of standard isn't enough. But to be fair to the regulators, we really haven't been able to give them enough information to target other things. That is coming, I should say. So this is Los Angeles. You'd think it was a long, long time ago. This is just 2002, and there are still days that look like that at times. So how small is what we call fine particles? PM 2.5 is what we call fine. This is a human hair blown up, a cross-section of a human hair magnified to 60 microns. And what you see, this to scale, you can see that a 2.5 micron particle is much smaller, much smaller than a human hair. 10 microns is correspondingly bigger. And so you can see that these are really small. There are probably 10,000, 100,000 per cubic centimeter floating around in this room, even though we can't see them. We can see some probably in the light that's shining in my eyes, because it's actually, the particles are what are scattering the light. And I should say that particles are what lead to visibility degradation, because they are so effective at scattering light. So where does PM come from? I promised, this is my one little lawnmower, which is a big one, and next time you go through the neighborhood and smell lawnmowers, you'll think of me. But there's a lot of different sources. Diesel trucks and buses are two that are in particular, major emphasis is placed on those in the state of California. One of our major contracts from the state of California is to differentiate between the emissions from cars versus trucks. It's literally $1 billion question if we can actually show which one is which, and I'll talk about that a little bit. Yard maintenance, meat cooking. You may think, meat cooking, Burger King, and other types of meat cooking operations. There were measurements made in the 80s that showed that cooking in the Los Angeles basin represented 30% of the fine particles in Los Angeles. So it's a significant source. We just got back from doing a study in Mexico City, and it's like 70% of the particles, the cooking that goes on down there, from what we were able to tell. Construction, power plants, wood smoke is a big one. One of our biggest concerns in the state of California is the San Joaquin Valley. The big source in the winter there is the combination of wood smoke plus fogs. And for that reason, any new houses that are being built do not include fireplaces in them any longer. So they've completely are trying to eliminate wood smoke in Central California. Wildfires is one that we can't always control very well. And then one of our favorite topics here is the impact of ships, which actually turns out to be pretty big in San Diego, and I'll talk about that in a bit. The other thing that can happen is you can get direct emissions. So when you see a tailpipe of a vehicle, you can see the visible particles. You can see black soot coming out of the back. But the other thing that can happen is that gases can be emitted into the atmosphere, undergo reactions, as I'll show in a second, with sun, basically, and form particles in the atmosphere. So you can get things that will start out in the gas phase and actually convert to the particles, and that actually represents one of the biggest sources of our air pollution, both in San Diego, all of Southern California, most of California, in fact. Sun is a major driver. So what this is called or termed is photochemical smog. So photochemistry coming from the sun. This is our little driver. He drives along and basically emits hydrocarbons, VOCs, also particles directly. And so you basically have these different species, the sun comes along, and that magical mix gives you smog. And this was discovered in the 50s by Ari Hagen-Schmidt at Caltech, where they actually, the first evidence they had was they were seeing the leaves on plants destroyed by something. And so they made a surrogate mix. You know, any one of these things by itself didn't work. You actually had to shine light on it, and then they could reproduce the effects, and that's unloaded a lot more research to try and understand the different sources of photochemical smog. So this is, as I say, by far the most abundant source of air pollution in California. But a lot of it turns out, we've done studies in San Diego, which I joked at first that there's really nothing here. There is. In fact, I'll talk about it in a second. On days there's really high levels of pollutants, and you can see them out over the ocean. And so a lot of times what happens, especially in San Diego, this is a map of the world. It shows air trajectories, air parcel trajectories of where air is coming from. And what you can see is that India and Asia, the continent particles are actually transported all the way across the ocean into the United States. So we import pollution from here and we export pollution out to Europe. So you can see that it goes out and comes back in over here. So we share. And this is a really important, this is actually a slide I borrowed from Professor Ramanathan. This had a huge impact because before these types of things were shown, I think people had a tendency to think, this country pollutes a lot or that country pollutes a lot, and that's their problem. But this shows you that it's everybody's problem, and this has caused people internationally to cooperate a lot more, which is a good thing. And it's what's necessary to get things fixed. So what are the different exposure routes that you face as far as pollutants? Well, during the day, air, water, and food are sort of the basic things that we encounter. And what you can see from this graph is either mass per day or volume per day, we encounter far more air than either water or food by mass or volume. So particles, as I mentioned, serve as transport mechanisms. They're how things can get into our body and get stuck there. They get everywhere. For a long time, we thought about particles predominantly affecting our lungs, and we were trying to understand that for a long, long time. And now people have started to find that there's a lot of cardiovascular effects and other diseases as well. And one thing that's a little known fact is that San Diego received an F from the American Lung Association for its poor air quality. So you may not, sitting here on the coast, most days are pretty nice, but as you move inland a little bit, especially as you get in towards Alpine, the geography gets you. You basically get a tremendous buildup of pollution, and I'll talk about that. You also have these highly aged particles come in from Mexico, from Asia, from Arizona. So we import a lot of pollution in San Diego, and I'll talk about that a little bit in a minute. So what about the entire state? How do things look? So the regulated pollutants are listed here: carbon monoxide, SO2, NO2, ozone, lead, PM2.5, and PM10. And what you see, this is, as you can see, a map of California for ozone, and what it's called, the thing we're looking at is areas of non-attainment. So these are areas that have such high pollution levels of a particular pollutant that they're not going to reach EPA standards. They're just too high. And so the non-attainment areas I've actually color-coded, and you can see for ozone, it's most of the state, including us down here in San Diego. We actually have pretty high ozone levels. So that's your traditional indicator of pollution. What about particles? Well, particles are actually, we're not completely sure the state of a lot of the regions. We don't know. Most of the studies, or the majority of the studies in California, we've done a lot in Central California, we've done a lot sort of down in LA, but there's these white areas that don't have any color. They're just the white areas, are actually regions that the jury's still out. We don't know whether they're going to reach attainment or not. But you can see, so there's one here that actually reaches attainment, but of the most areas that we know something about, they're considered non-attainment areas. And there's a good chance that the trend will continue as we go through a lot of these other regions. These regions out here are regions where there's high levels of dust, and we're struggling right now, as is the rest of the nation, what to do in areas where there's just a lot of suspended dust. This could be huge health problems. Nobody really knows. And so this is a pretty hot research topic in air pollution right now. So what is the air pollution climate link? Well, probably most of you have seen this cover page of Time, which came out, I believe, in April of this year, and it's cause for alarm, and I hesitate to give sort of a doom and gloom perspective, but I think it's important to think about where we are. And the part that sort of stands out to me is that we're past the point of being able to think about what to do. I mean, the temperatures are rising, and we're sort of at, as people like to refer to it, as the tipping point. I constantly, when people hear what I do, say, is it warmer? And I think most of you in this audience probably know this, but 10 of the 11 hottest years on record have occurred since 1995. So yes, it's getting warmer. 2005 was the highest temperatures we've achieved. And so, as I say, I think everybody in this room has seen this, but I do want to talk about sort of how can we help with the measurements we were making in sort of coming up with ways to make things better in our future. So as far as climate goes, the greenhouse gases, the standard ones that you hear about, carbon dioxide, it's been measured. There's a great tradition here at Scripps. Keeling, the famous Keeling curve measured CO2 since 1958 at Mauna Loa, shows that this is increasing. Basically all of these are increasing, and we have a pretty good handle on the rate that they're increasing and the effect that they're having on climate. They're warming our atmosphere. Aerosols, on the other hand, we don't. Aerosols basically can either warm or cool the atmosphere depending on what they're made of. And so what you'll hear a lot about, and you've probably heard about, is that aerosols can scatter light very effectively. In particular, everybody's favorite is sulfate aerosols. And one of my sort of, I guess, claims to fame is to try and sort of get rid of this misnomer of sulfate aerosols, because they do not exist very often in the atmosphere, and I'll talk more about that in a minute. But they will scatter light, so basically they've been offsetting the warming. And so people will say, well, let's just inject more sulfate aerosols. And so, there's actually a paper by Professor Crutzen, one of my colleagues, on this sort of thought process, which is interesting. If anybody's interested, let me know and I can pass it your way. But the other thing that happens more commonly is that aerosols warm, and in particular soot. You look at soot that comes out of a tailpipe of a truck, it's black, it's absorbing, it's warming. And so basically we can get warming. At the center of every cloud drop is a particle. And so certain particles form great clouds, and if most of you have flown over clouds and you look down, you see this white reflection coming back up. That's light being reflected back into space, and that's a good thing because it doesn't get down to the Earth to be re-emitted and absorbed and lead to warming. So that's another sort of potentially cooling process, although clouds can also warm. That's a lot of details, but it's important to recognize that it's not a simple issue. And so the other thing that happens is, depending on clouds, you can talk about the global implications, but what's been shown again by one of my colleagues, Professor Ramanathan, is that these clouds will actually affect local weather patterns. And so in certain areas, such as India, where there's a lot of air pollution, they're actually suffering from drought. And so there's a lot of issues with, how are these particles affecting climate? And this sort of issue of how particles contribute to climate change from the standpoint of what's called the indirect effect is the single largest uncertainty remaining in our understanding of climate. So how aerosols impact climate is really a wide open area. It's getting better, we're understanding more and more, but when you start talking about uncertainties, this is one of the primary causes. So coming to this issue of climate, how it's linked with air pollution and health, you can see here that this is our ozone, which is a traditional indicator of pollution. This is the California standard, this line right here. And what you can see is that as temperatures rise, we get more pollution days. As we have more pollution days, we have more health effect problems. And this is, I want to point out, this is specific for the state of California. This isn't the United States. And if you look at the numbers, they're pretty astonishing. This is the annual basis. We have 8,800 extra deaths per year attributed to pollution. 7,100 hospital admits, 3,100 for cardiovascular, respiratory. Asthma is a big one, and then just 4.7 million school absences due to respiratory problems. And so this is a great slide for sort of showing this link that I mentioned between, as things get warmer, we get more pollution and more health problems. So they are all coupled. So my research group focuses primarily on aerosols. When we go out and make measurements, we measure pretty much everything we can, but our sort of unique piece of measurement equipment focuses in on individual particles, examples, dust, smog, fog, a lot of different viruses, pollen. Our major research goal is to be able to actually figure out where these particles are coming from. How are they actually forming in the atmosphere? And we do this through a combination of lab and field studies that we've conducted everywhere. Lots in the United States, more in California than anywhere else, as well as other regions of the world with colleagues. I should mention, there's a lot of researchers at UCSD that focus on aerosols and climate. They're usually on these big studies with us as well. So it's a nice, I think at UCSD, for aerosols and climate research, we have the largest collection of anywhere in the world, which is exciting. So as far as my research group goes, I mentioned one of the goals is to try and understand this link between air pollution, climate, and health. They're intricately linked, and so we might as well tackle them all at the same time. Initially, I spent the first 7 years trying to develop instruments because the measurement techniques were just not available that would get us to the next step. So we actually have our own machine shop in my group. My husband happens to design my instruments and build my instruments. I always say, if you find a good machinist, marry him. And I did. And if he does a bad job, he has to sleep on the couch. So my instruments are really nice. And so basically, we focused really hard on just getting these newfangled instruments going, getting them accepted as being, giving us something useful. And then the excitement has begun. In the last few years, we're able to use these instruments to actually solve problems, which is a nice feeling. And so we measure the size of individual particles. So I'll talk about the other way you can do things, but we measure the size and the chemistry of each individual particle. So we can measure, in a study, we will measure the chemistry of millions of particles in the air, and we get the information instantaneously. So it's one of the only instruments, maybe the only instrument, that you can actually turn on in this room and know what you're breathing instantaneously. And that we finally have achieved sort of the long goal to get to that point. There's still sort of bugs and kinks to work out, but we've gotten very, very far, very, very close to this. The neat thing about it is that normally what you do is you pull a sample onto a filter, and it's trapped there for hours to days and stuck in a freezer, and then you pull it off and you analyze it by a variety of tools. And a lot of times you have changes. And so when you finally get to the point of measuring the chemistry, you don't really know if it was some sort of artifact from your collection process or something that actually told you something about the atmosphere. So getting away from any sort of sample collection has been one of our primary goals. Now there are trade-offs. Having things on filters, if you have extra questions, you can go pull the filter out of the freezer and do further analysis. So we go back and forth between both. I mean, we use filters alongside of our measurements during most studies. One of the things we hope to do is to provide new inputs for climate models and help reduce some of these uncertainties, and then also figure out what are the things we should be controlling. So traditionally, particles are floating around in the air. They get pulled with a pump, land on a piece of filter paper. You collect things for usually a long period of time to get enough material to detect anything, and you get sort of the average of everything that was there for that 4-hour, 8-hour, 24-hour period. And so I'll show an example of the data in a minute, but to try and unravel what really happened in the atmosphere and where the sources came from is really challenging. And as I say, it was a major stumbling block. So one of the things we try to do is maintain the integrity of each individual particle, and from this we can sort of say, if there's a bunch of the purple particles, say, that came from, say, diesels, we can start correlating these, hopefully making correlations between high levels of very specific particle types with health effects. Similarly, for whether they're warming or cooling, I'll show that on the next slide. How they age in the atmosphere, different particles. One of the things we do in my group is we study dust. And I never thought I could get so excited about dirt, but I am. There's a lot of dirt in the atmosphere, and it turns out that if it wasn't for that dust in the atmosphere, our atmosphere would be completely different. The surfaces of those particles cause things to react and change that wouldn't happen if they weren't there, and we know very, very little about those processes. So one of the focuses in my group is to try and understand those processes. We've done the atmospheric observations in regions over in Asia where there's incredibly high levels of dust in the spring, and now we're going back to the lab, running experiments and trying to understand a lot of the chemistry, and then put that into models that will predict sort of how the particles are affecting our pollution. So one of the things I like to point out, if you go back to this piece of filter paper, is why do we want to measure one particle at a time? It's what's often called mixing state. In other words, we look at which species go with which. And this is really important from a climate perspective, because certain species are scattering and certain species are absorbing. In other words, certain ones are warming, certain ones are cooling. So let's give you the two examples. Elemental carbon, or soot, black, as I've color-coded it here, absorbs very strongly, as I mentioned. Sulfate, as I mentioned, scatters very strongly. So the question is, does every soot particle, if you had, you weighed these, you saw that there was 90% of the particles were composed of elemental carbon and 10% sulfate by mass, does that mean that every single particle looks the same, which is what you basically have to assume on a piece of filter paper? Every single one has soot combined with sulfate? Or in fact, do you have one pure sulfate particle and 90% soot? I mean sulfate, 10% sulfate and 9 soot, 90% soot. And so why do I care? Well, the optical properties, the warming and cooling properties of these two scenarios are dramatically different. If you take a soot particle, which is an absorber, and you coat it with sulfate, intuitively you might think, I did, that the sulfate shields the soot and actually could convert the soot to a scatterer, to a cooler. But in fact, there's been papers written that the sulfate actually focuses, in an optical effect, focuses the light into the soot and makes these particles 10 times more strongly absorbing than pure soot alone. And so one of the key questions we've been asked to look at with our measurements around the world, and we're now writing a synopsis on this, how often do you actually have this scenario versus this scenario? Does all soot have sulfate? I can tell you the punchline is yes, for the most part. Very rarely do we ever see pure sulfate particles floating around. I would say 95% of the time, we see the aerosols are absorbing. And what I think happens is if you do get a pure sulfate particle in the atmosphere, there's so many other pollutants that they combine, and you end up with this scenario very quickly. So if you have, a volcanic eruption, you'll see probably lots of these for a while, but they will change very quickly. So this is really one of the main things that we're interested in. This is the instrument that we've developed. This is a picture of the first generation commercial instrument that a company has taken on. And basically, particles are floating around. This instrument is under vacuum, so the particles get pulled into the instrument. They go through a laser. They scatter light, as I mentioned. And so we know the particle has passed through here. They go a little bit further. They scatter light again. We measure the time it takes for that particle to go between those two lasers, so the time between those two scattering pulses. That tells us how fast the particle is moving, which does two things for us. If we know the exact position of the particle in the instrument, we can time a pulsed laser to desorb and ionize the chemical species from that particle. We actually get the positive ions, different things like to be cations, and the negative ions from each sized particle. The size information, stepping back, we get is smaller particles move faster, bigger particles move slower. So we now can correlate size and chemistry, which is really important when you're thinking about the optical properties, the health effects, etc. So just to show you a couple just fingerprints. I'm not going to go through all the details, but this is one of our favorite ones we see in San Diego. Sea salt, just ejected, sea spray, dries out. We end up with cations, sodium chloride as you'd expect in the positive ion, chlorine in the negative ion. This one actually, nitrate, is some amount of reaction that should be NO3 minus. And so just to show you, this is one that's been pretty much just emitted from the ocean. If you compare that with one that's been floating around for a while, you can flick back and forth. You start to, as I mentioned, it starts to become a sink for a lot of other pollutants. And so you can start to watch these particles age and see how particles are actually influencing the atmosphere. So just to give you a flavor for comparing the traditional method with a filter versus the aerosol time of flight mass spec, we take different sources, like in this case a ship. And so a particle goes in, we get a distinct fingerprint for that particular source. We can do cars, we can do trucks, sea spray, biomass. And what happens is we run as many sources as we can, and we make what are called libraries. We take those fingerprints that I was flashing, and then we're ready to do atmospheric sampling. And so we do atmospheric sampling, and in real time we're seeing this literally flash by. The filters can collect. We're not really sure what's on there yet. And so this will continue for however long that you need to collect on filters, but we're actually, as I say, getting real-time information. The interesting thing about the particles suddenly lose their individual identities. They become sort of this mixed up blob. And what happens is, basically we take these back to the lab, and 4 to 6 months later, we have the answers from a variety of instruments of what was present in the atmosphere. And I'll show you the different form. Whereas we're able to basically instantaneously say what's there at a given time. So just to show you what filter data looks like, this is data taken out of a paper where there was 29.6 micrograms per cubic meter. That's the mass that I was telling you about. And what you see is sulfate. So there's the sulfate type. There's elemental carbon, which is soot, organic carbon, carbonaceous types, others, crustal, ammonium, and nitrate. And if you think back to what I was mentioning, we look at the associations of these particle types. From this information alone, let's say there's a lot of sulfate here. Why? We don't know the source. We don't know which particles it was on. It could have been on the dust or the sea salt. And so there's a lot of information that we don't know the answer to as far as what are the sources that are changing these pieces of the pie, and we sort of get stuck at this point. To compare that with the information we get from single particles, this is the size resolved chemistry from 0.2 microns up to 2.5 microns. One thing that jumps out at you, we now have labels for very specific sources, and those sources show very different chemistry. Below about a micron, we have mostly the combustion type particles, cars, trucks. In this case, this is actually data we acquired in India where they had a lot of biomass burning aerosols. But you can see that in the larger particles, which actually weigh a lot, there's quite a bit of sea salt and dust as well. And so these make up a large fraction. On really polluted days, what happens is these carbonaceous aerosols get so big that they grow out and they fill in this mode. So this is sort of a relatively low pollution day. But the interesting thing to compare is sort of the difference in the categories, which here are source specific versus here are sort of these nebulous categories that we don't really understand what goes with what. This is a busy slide, I realize, but it's one of my favorites, so I have to show you. This is a study in Riverside where we can go back to the pollution and see if we understand what's going on. This is one of those pie charts, but every hour. And so looking up this way, you can see the green is dust, the blue is sea salt, the black is vehicles, orange is biomass, or is actually aged organics. Wood smoke is this magenta color. And this is over the course of a month. And what you see is, you know, sometimes dust is dominant, but what happens is you get this yellow is the mass concentration. And what you see is over the period of days, you get this buildup of large levels of pollutants in Riverside, and then they fall out. The mass concentrations crash and sea salt. So it's a good thing that Riverside is close to the ocean, because every once in a while, this sort of buildup gets washed out by sea salt coming in, cleaning things out, and then you get the buildup again. And so you can see this happen over and over, especially during the summer. During the summer, you have these oscillations every single day. The winds from the ocean come in and clean things out every day, which is a good thing. And then out here, you can see dust dominates with wood smoke. This is actually during Santa Ana's, and this looks very similar to San Diego during Santa Ana's. So what about San Diego? This is where air is trapped. We have, again, what hurts us as you move further inland is you have just plain old geography. Air gets trapped, you have basically an inversion layer form and keep the pollutants down close to the ground where we have to breathe them. So where does the pollution come from for us? Well, it can come from the desert, as I mentioned, Arizona. It comes from Mexico, LA, Asia, as well as the ocean. So at any given time, we can get air from any of these regions. And one of the things we're trying to understand, because I should say the air quality in San Diego is one of our least understood ones in all of California. So we're working hard to try and understand, you know, which major sources and from where are these pollutants coming. One of the major sources, as you might imagine, of pollutants or particles in the atmosphere are the sea spray, as I've mentioned. And so how this works is basically you have this bubble, it goes up and bursts, and you get individual sea salt particles. But the concern is when you're in a coastal environment, and this is a real concern, is that you get runoff. You have a harbor, you have pollutants in the ocean. I think a lot of people think the pollutants go in the ocean and they stay there. But it turns out that a lot of these pollutants don't like water. They're what are termed hydrophobic, and they want to get out. So they hitch a ride on this bubble, the interface between the air and the water, and they get enriched up to a factor of 10,000 times in the air. And then the air carries them to us. And so if they remain in the ocean, that's one set of environmental issues to deal with. But a lot of them are getting out and coming to us. So when they shut down the beach and they don't let you go swimming, again, you'll be thinking of me, but you probably don't want to be walking on that beach for a while either, because a lot of the pollutants are being bubbled off and brought to you through the air as well. And this is an area that we're really interested in. So how do we study this? This is one of the studies we've gone out on the Roger Revelle. This is a van right here. We put all of our instruments in. I mentioned this is one of our instruments. This is Elwood. So our instruments are conveniently named. We have Jake and Elwood and Laverne and Shirley. And And so, my students take better care of them when they have personalities. And believe me, they have personalities. And my students like fall in love with Jake or Elwood and swear that that instrument loves them more than someone else. It just creates more personalities in my lab, let me tell you. But anyway, so this is one of our instruments on wheels, as you can see, so we can roll it into the cart. But we look at gas phase species. We measure particle sizes. We look at cloud properties of the particles. We also make radiative measurements. So we do the combined suite of measurements when we go even in this little crate. The other thing we did recently, and we hope to continue doing, is we put our instruments in a trailer, which if you've been out on the pier you might have seen. This is a sampler, an air sampler, a MET station, and inside here is that whole combination of equipment. This is one of our instruments. This is the gang who worked on it. The two key people that spent, well, three key people that spent a lot of time on it were Andy Alt and Megan Moore. Also, Hiroshi Furitani is really interested in how clouds form, and so he spent time. And then John Holacek and Matt Spencer have helped basically keep things going, and they've been involved a lot in our international studies. So what is our dream for this pier? Is basically to do long-term measurements to be able to say something about how the air changes in San Diego and get a better handle of our air that we're actually breathing. As I mentioned, we get paid to go all over the globe to sample other people's air, and I finally decided it might be a good thing to know about the air that we're breathing more often than not. And so the pier is a really good location for that. And basically, what we hope to do is establish it as a state-of-the-art place that other people can bring sort of new technologies, and we can do coupled aerosol, climate, air pollution type measurements, and get a handle on how these things are changing over time, and do certain tests to basically use this as our site. So one of the first questions we've been asking is, where is the local air pollution coming from? I'll come back to that. And another thing is, once we know where it's coming from, how the heck do we control it? Well, one way we can control it is California is deeply interested and works very closely with us, and so we can work with the state of California. But we've also recently had Professor Mario Molina come to join our faculty, and he has links with Mexico. And so basically we know a lot of the age pollutants we get are from Mexico, and vice versa, we send some down their way. And so the question is, can we work with them to sort of to catch Mexico, because their regulations are much further behind the state of California. Everybody's further behind the state of California. And so can we work with them to sort of start to control some of these emissions? And then, as I mentioned, California is easy because CARB, the California Air Resources Board, is the most aggressive state in the nation by far on air pollution. So what have we learned so far? Ships do have a major impact. We've actually been tracking ships, and it's not just the ships, it's actually rarely the ships in our own harbor. It's a lot of times coming from the LA harbor. When the wind comes down the coast, we get a lot of pollution from ships. They burn the dirtiest fuel, and so it puts a lot of stuff up, and it's a concern to the state of California. There's international ships. How do we control this? I mentioned vehicles. Really, in the state of California, vehicles usually dominate, but in San Diego we see a lot of wood smoke, especially in the winter. I mean, people in the summer at the campgrounds are burning campfires to keep warm. I don't know, but maybe roast marshmallows, I guess. But we see a lot of wood smoke in San Diego. As I mentioned, we see quite a bit of long-range transport. We did a study, one of the studies where we were trying to differentiate between cars and trucks. We parked our instrument next to the 5 freeway, and we sat there for a month. And we were trying to measure the fraction between cars and trucks, and we thought, okay, we're right by the source. This will be easy. And it actually turned out to be really hard, because there was so much pollution sort of imported from other areas that the amount from the freeway was this little ripple on top. It was actually a pretty small amount. And so we are importing a lot of pollution, which makes sort of figuring out how to fix it a little bit harder, but we're working on it. And one of the things we would like to do with the peer type study is, have basically a broadcast. If you want to know what the air quality, what's in the air you're breathing today, you can go, or at that hour, you can actually go look at the data. And this is something we're working on with Cal IT too. So the questions, how are these different sources impacting our health and regional climate? How do they vary spatially and seasonally? So that trailer I showed you is actually a mobile lab funded by the state of California. We're now going to drive that around San Diego. So if you have any favorite spots where you think there's lots of pollution, let us know, because we're going to be sneaking around with our white trailer. But if you see it, you'll know it's us now. So we really want to try and understand the variability. If you live in this neighborhood, somebody lives over here, is somebody being exposed, are you both being exposed to the same level of pollutants. And that's a major question all over the state, but it really hasn't been looked at too much. So where do we stand? We're making major strides. Really, we are in understanding the sources of air pollution. And I think, we're lucky to be in the state of California, as I'll mention, and I'll follow up with this, because they're just so aggressive about this kind of thing. We don't wait for the federal government. We do it as a state. The other states follow, and the rest of the world follows. California has set some of the best guidelines for air pollution that we have, and now they're doing the same thing for climate. Determining which sources impact climate and health, we also have to look at other measurements. So I mentioned we have a suite of measurements. We work with a wide range of investigators from both UCSD, Scripps, as well as all around the world to solve these problems. And it really takes an interdisciplinary approach to do this. We're working with California regulators. As I've said before, they're open ears. They've been great in supporting. They supported our first development, our very first instruments that weren't even tested because they knew they needed to get something besides the filter methods, which says a lot. I mean, I don't know another state that would have funded those instruments. So the question is, where do we go from here? There are two scenarios. You hear them. I mean, a lot of people will say, let's fix it now. It's going to cost a lot of money to fix it now. So there's some hesitancy. We can either admit that there's, changes happening from an air pollution, from a climate perspective. And the question that you have to ask is, what happens if we start reducing the emissions right now and looking at alternative energy strategies? Well, one thing that can happen is we will immediately see an effect in the air pollution and the health effects. We'll reduce the strain that our system, that our environment is under right now. The aerosols are sort of almost what are sort of pushing things over the brink. They're relatively short-lived, and so if we can even reduce those a little bit, I think we can give the system a little bit of a break. And as I say, we can impact the air pollution now. The harder part to fathom is, what are we going to do to our future? We know we're going to help the future, but the future's way down the road. I mean, the warming, the changes we're seeing now are from what people put in the air 50, 100 years ago. Our pollution's not going to be felt till, the middle of this decade or century. And so, and it's particularly going to take off. We really worry about the end of the century. So we really worry about what we're doing for subsequent generations. What happens if we wait and see? A lot of people are pushing, not as many now, are pushing to this wait and see approach because it's, it's not like the ozone hole where it was an immediate, obvious thing that was going on. Although I think we're starting to get there, but it's sort of on a slow part of the slope. But it's going to take off, and we need to do some. I think, my personal opinion, and I think many scientists' opinion, is we need to do something. And so when you ask what happens if we wait, this is a report on changing climate. Dan Kahan from Scripps was actually one of the authors of this, and it talks about sort of the temperature changes we can expect to see possibly by the end of this century. And you can see that it could be as much as 10 degrees Fahrenheit. And so what things will happen, I heard the speaker for next time is going to be on rising sea level. In the best scenario, the very best scenario with this, these uncertainties we have of how much warmer it will get. Not whether it's getting warmer, but how much warmer. The lower warming range, you can see we still are expecting a 6 to 14 inch sea level rise by the end of the century. And you'll hear more on that. But there's a variety of things. A lot more warm days. You can see the medium scenario says that if you have a lot more warm days, you're going to have more forest fires, which I think we're already experiencing. Up here, it gets even almost too scary to read. But it could fall anywhere in here, depending on what we do today, hopefully. So in line with that, as I mentioned, the state of California, luckily, is incredibly proactive. And so, I don't know how many of you heard about the bill that was recently signed, AB 32, but it's looking at global warming solutions for California. And as I say, the good news is they're thinking ahead. They're not waiting for the federal government to sign the Kyoto Protocol, which who knows if that will happen. And so, we're, as a state, going to go after reducing our emissions of greenhouse gases. The goal is to reach 2000 levels by 2010 and 1990 levels by 2020. I should also point out the students at UCSD are great, and it is their future, and they are actively working in a variety of different ways to push UCSD and the entire UC system to sort of lead the charge in this, which is exciting. This is the list that California gives for the things that they're going to try and do to cut global warming pollution. Energy efficiency is top. I mean, we're always talking about alternative energies. We need to do a better job at just using the energy that we're already producing. I think that really has to be a first, there's a reason it's number one. But you can go down through the categories, and there's a lot of different ideas that people have, and it's going to take some combination of all of them. So in conclusion, we're all in this together. Everybody needs to take a proactive approach. I try not to give sort of the gloom side. I mean, I think there is a positive, and every single person can make a difference. If you think about it, if each person just did one little thing, such as change a light bulb, it's equivalent to removing 3.5 million cars off the roads. If we plant a tree, it's equivalent to taking basically they will soak up the CO2 from an SUV that's driven 26,000 miles in a year. So there are things that we can do, just little things. I mean, I walked by one of my neighbor's houses, and they'd cut down this tremendous orange tree, and I just felt terrible, and I wish I would have told them, here, plant it in my yard, but there are things that that everybody can do. So I'd like to acknowledge the team. I just have an incredible research group of graduate students, postdocs, project scientists. I also want to acknowledge my little guys, Joey and Nick, and my husband, Joe. There's a lot of people that aren't in this picture, unfortunately. We've got to get a new group picture. Funding, National Science Foundation has been incredibly kind to us since the beginning. EPA, as I mentioned, the state of California, through the California Air Resources Board, have funded the research that I talked about. My personal motivation are these two guys. I mean, I'm going to see a little flicker of what's going on. We already are, and it's going to continue. But these guys, I want to keep these skies blue for them and for their kids. When we think about the choices that we make today, this is a picture of my son Nick. He's looking in a tide pool, and this picture just struck me because, I just really, people, Nigella mentioned I work too hard. I do, but I work hard because I feel like we can make a difference. And, looking at this tide pool, I really want, I know these tide pools, in all honesty, have changed since I, was the little person looking down in them. But I want his kids to be able to see the tide pools and other kids of their generations. So with that, I thank you for your attention, and I'll be happy to answer any questions.
One of the pollutants you mentioned in one of the first slides was CFCs. Can you tell us what they are?
Oh, I'm sorry, chlorofluorocarbons. So those were the refrigerants, right, I'm sorry about that. I was probably off from my class. But yeah, so they're the refrigerants, the things that led to the destruction of the ozone hole. Yeah.
I wonder whether it's premature to ask whether some of these microscopic things that we're just now discovering have had some role helping other forms of life throughout the geologic past, or even now. In other words, you're talking at the high end of the tree, the organic tree.
Right.
Do other things that feed on these?
Yes. Yes, that's a good question. So, one of the best examples is just dust deposition, nitrates to the ocean. They are great as far as keeping biogeochemical cycles going. So he was asking if the dust and things floating around actually can in essence help things, right? I mean, it was basically your question, and the answer is yes. There are good things that particles do when they deposit, for example, to our oceans, to our soil, absolutely. And we understand that kind of. We're trying to do a better job, especially in the area. Kathy Barbeau, who's a professor here, is working on iron deposition and how that feeds phytoplankton in the ocean. There's a lot of research going on in that area. So understanding it well, not yet, but it definitely, there are good things they do as well. That's a good point.
I was just wondering if you got any interesting measurements after the grounding of all aircraft after 9/11.
We did. We actually made measurements. We did the two interesting events we've had since we've been down here were the grounding of the aircraft, and then, which we were hoping to look sort of for a lack of signature, because we don't know what the I should ask this question. We saw anything interesting when the aircrafts were grounded after 9/11. So the absence of a signal. We took the data. We actually haven't looked at those data yet. The data that we did look at, the interesting event, were the wildfires. And those were, we just are publishing a paper with other Scripps researchers on the impact of the wildfires in 2003. So yeah, there's been a couple of interesting events. So we still have to go back and look at that. We did flip on the instruments, but we don't know yet what the story is. So the question was, are there still particles floating around from Mount St. Helens, and are there natural processes that clean the air? And the answer to your question is sort of, volcanoes in general are constantly kind of puffing up particles. And so, in fact, we saw this a lot in Asia. We went by a semi-active volcano, and we can see the signatures from volcanoes. They last. Particles from volcanoes, in general, particles in sort of this micron size range can last for a couple of weeks. And so we can see the signatures from particles from volcanoes that are just not even, blowing their tops off. Usually if a volcano explodes and you sort of look at the particles from that volcano, such as Mount Pinatubo, it actually cooled things for a couple of years. We saw an effect. So they can last have an effect for a while. As far as cleaning goes, a lot of particles are scavenged very effectively in rain, and also by clouds. And so you can rain them out, and that's what leads to, for example, if it's acidic, you can get acid rain from that. But if you've noticed, especially in Riverside, when it's really, really polluted and it rains, and then you look outside, it is the most gorgeous place around. You've got these gorgeous mountains. So yes, they're very effectively scavenged by rain and clouds and also snow. Yeah.
Last question, please.
I want to go home and change all my light bulbs.
Good. I am glad to hear. I'm glad I gave this talk.
Are there any kind of special things, just those spiral things?
Those spiral things, and I have to put a pitch in because my husband changed mine about 5 years ago, and I made him change them back. I have to admit, because the yellow hue I didn't like, but they've gotten much, much better. So all of mine are changed, and that's all I've got. So I don't know the difference anymore anyway. But yeah, I should say the technology has changed a lot in the last few years. So, thank you.
Thank you very much.
Okay.
That was wonderful.